All right, take it away.
Well, good morning. Let me share the screen and get going here.
We had a comment that meteorological spring starts March 1st every year. So I got one person in the spring starting now camp
Okay.
along with me.
Check here. There we go. Yes, welcome to Tom Talk. So the subject for today and what ecology tells us about the living world is a collection of ideas that I've sort of run across over the years, reading popular science essays and just studying ecology and experience the world and teaching and listening to people's questions. So it's both about what ecology and science in general can tell us about the living world and kind of what it doesn't. Both of those things are important. It's divided into a number of topics that don't have any scientific organization here, but it's we talk about growing, being a descendant. In other words, a little bit about evolution and descent, being the right temperature, being the right size, being big and small, just being. I mean, what is it? What are the dimensions? What is a plant or animal? How do you know when they start or stop? What is it to be an individual? Then eating. It's a messy world, is how the world is organized. And then what is normal? So all of those sorts of topics we're going to talk about today. And the first one is growing. So this comes up, it's kind of a plug for the next Tom Talk at the end of March on Charles Darwin. He has a point pretty early in the book where he's talking about reproduction of organisms and talks about reproduction of elephants, which he reckons is the slowest breeder of all known animals. It will be under the mark to assume that it breeds when 30 years old, goes on breeding till 90, brings forth 3 pairs of young in this interval. If this is so, by the end of the 5th century, there would be alive 15 million elephants descended from the first pair. So growth of populations. I mean, you've probably run across this before, but I want to look in a little bit more detail because I don't think most people really appreciate what exponential growth actually means and to look at the reality of exponential growth. And it explains some of the puzzling phenomena that we all experience in looking at the living world, particularly if you see it from year to year and you see changes happening. So what is exponential growth? Well, that's why your mother and father told you to invest early, which I never did, to put your money in the bank because it grows over time. So if you invest, $100, and well, this goes all the way out to 250 years, but even if over 50 years, that $100 turns into $1,000, yes, into $1,000. I think that's actually should read 100 years. It turns into $12,000. So it grows over time, and you see by the shape of the curve, it grows faster and faster and faster the longer it's in there. So getting your money in early, had I been wise and invested some of my $1.25 an hour job I had when I was a senior in high school, I could be a rich man now, but that wasn't the case. So what point I want to make here is it's a constant rate of growth of 5% of whatever is there last year. I get 5% more this year. And that seems like just adding a little bit at a time, but you can see that results in this curve that bends up sharply the further out you go. So let's look at just some comparisons here. And just could be investment or could be the growth of a weak population, which we'll talk about here in just a second. On the blue line is showing you, we'll just say that's the original one and that it starts growing at time 0. And the orange line starts growing just 10 years later. And you can see that not only is the blue line always above the orange line, but it gets farther and farther and farther above. The gray line here is the difference between the two. So the difference between these two gets bigger and bigger and bigger and bigger over time. And likewise, if we look at two investments or two different weed populations that are growing, if one is growing faster than the other, let's say the orange weed population is growing faster than the blue weed population, not only is there more of the orange weeds than the blue weeds, but the difference between the two gets bigger and bigger and bigger, faster and faster and faster. So in the beginning, you wouldn't notice much of a difference between the two. If you come back in 100 years, you'd notice that one is blanketing the country and the other one is not nearly so abundant. This is Darwin's elephants. I'm just going to look at this at a number of different scales. So this is looking at Darwin's elephants at a scale of just over a century. You can see that the rate of growth is the steepness of a line. So here it's the elephants, over that first 20 years, it doesn't seem like they're really doing very much. They're just starting. And then as you get toward the end of the 20 years, you notice, well, the population seems to be growing faster. Well, if I look at it over 200 years, now the line looks different. Well, I don't see anything happening in the first 50 years, whereas before it seemed like the first 50 years they were growing quite a bit. Same line, just looking at it at a different scale. We see that most of the changes out here between 150 and 200 years. That's when it's really starting to grow. And if we look at it over a 500-year interval, it looks like nothing is happening over the first 350 years. And then suddenly the curve goes up. This is the property of exponential growth. This was a weed population. Of course, you wouldn't live to be 500 years, but you could make this 5 years. Somewhere between the 4th and the 5th year, you'd say, well, something must have happened. Something must have happened. That weed population exploded after the 4th year and before we got to the 5th, but it didn't. It was the same curve all the way along. It was growing right from the first year. It's just that the difference being that whenever you notice it, it seems that's when its population growth reaches your consciousness, and then you think, something must have happened. But what actually happened is the weed was introduced at a certain point in the past, and its growth has finally reached a point where you see it. It's always been growing at the same rate. Here's our friend garlic mustard. I don't see it. I think because we're being a little bit more careful with landscapes today, these are less than they used to be. These just massive outbreaks of garlic mustard, but there's still plenty in sort of what these are pretty scrappy woods here. So where does this come from? Well, if we look at the growth of a garlic mustard population, and now the line looks straight, but if you look at the scale on the left-hand side, you can see that it's now what we call a logarithmic scale. This isn't going from 1 to 2 to 3 to 4 to 5. It's going from 1 to 100 to 10,000 to 1 million to 100 million. So it's going up by a factor of 100. And when you graph an exponential curve on a logarithmic scale, it turns into a straight line. And it turns out if garlic mustard plant, a big healthy garlic mustard plant creates 1,500 seeds and half of them germinate, and every one of those grows into another plant, garlic mustard would cover the entire dry land surface of the earth in about 6.5 generations. It's a pleasant thought. Of course, that's a thought experiment. The seed dispersal in that couldn't reach and it couldn't grow in Antarctica and all of that. And just the point here is just how rapidly a garlic mustard population of any organism can spread exponentially. We could slow that down and just have the garlic mustard population double every year. And now it would take a little over 50 generations. It's 2 years for a generation of garlic mustard. So you're talking a little bit over a century before it covers the entire earth. And this is what, if in this case, we're talking about 750 viable seeds. So we're saying that 748 of those seeds die. Only 2 survive, and yet the population still covers the earth in a century. We'll come back to this idea of exponential growth when we talk about Darwin at the end of the month, because this becomes a really, really important part of how he really revolutionizes our understanding of life, of this potential for exponential growth, and therefore the resistance that the environment offers any organism. So obviously, if there's a large resistance to population growth, almost all the offspring die, even in a problem weed like garlic mustard that you keep fighting with, and it seems the population seems to be growing each time you go out there, or you can't get rid of it. Still, almost all of the seedlings are dying every year. You just notice that the number of adults remains the same. And so I ask you a question here. Which would you do in trying to control garlic mustard? Would you try to collect and kill all the seeds? Would you try to kill all the seedlings? Or would you try to kill the adult flowering plants? Well, if you tried to kill all the seeds, that would be pretty hard because there's 1,500 for every single plant. So that would be almost an impossible task. The seedlings, I mean, and I'm not talking, garlic mustard is a biennial. So at the end of the first growing season, you have a nice not nice, but a rosette. But of those, that rosette is one of probably 100 or 500 germinant seedlings that you had earlier in the spring. If you actually look for them, they can be almost covering the ground, tiny little germinant seedlings, almost all of which die. And we tend to focus most of our efforts on the adult plants because there's so many fewer of them that it makes it much easier to control at that life stage. And we try to keep the population low because as the population gets big, it grows even faster. So it's easier to maintain the population at a low level than maintain it at a high level. We have to work much harder to maintain it at a high level than a low level. So when you control a weed, you want rapid identification and early control, right? You want to find it before it starts to get very far along that exponential growth curve. And you want to improve the native plant community because that, in a sense, if we're talking about money, you're lowering the rate of return. You're reducing the rate of population growth when you improve the native plant community and allow less space for the weed. And we try to maintain those weed populations small in order to lower their growth rates. I mean, we sort of arrive at this by just practical experience, but it makes perfect sense when you look at how populations grow. We're looking at the flip side of it, and we're looking at species reintroductions. After 20 years, we want to have a nice, big, abundant population of native plants. And we have two variables. Well, we'll simplify it to two here. It's when we introduce it. What date do we introduce it? Obviously, if we started it earlier, you would get to the goal faster. And it's how fast do the populations grow? Well, when we looked at this on the right hand or both sides here, you can see that starting earlier, the curve always stays ahead of the population that starts last. But if you look over here, the gap between the two is much larger. So by manipulating the rate of growth, you're going to be much more successful in growing that population. So therefore, it makes sense to take time to do this, the site preparation to get good seed germination and really get the population off to a fast start, because that rate of population growth will have a much bigger effect on the prairie plant populations later on than will just starting 1 year earlier. So while both of them, obviously starting earlier is better than starting later, but having a good seed bed is even more important. Okay, now we're going to switch and talk a little bit about being its descendant. We're all descendants. I mean, life on Earth starts, as far as we know. I think they pushed it back to about 3.8 billion years ago, and life is really a continuous, uninterrupted stream ever since then. Life never started again. It started only once. And we just have life going from one individual to another, to another, to another in evolution, sort of introducing new species along the way. So the basic question, I think I asked this in the the blurb for this talk is, why do I have 5 fingers? So is it to throw a spear better? Maybe to use a bow and arrow better? Obviously, our fingers come handy for lots of things. We all use keyboards today. I'm probably one of the slowest typers on earth. I could use maybe a 6th or 7th finger, really. Might help me out a bit with a keyboard. Or, which I find very useful for scratching my head, because I'm often puzzled about things. And I think this is actually true of other primates, that when they're puzzled, they scratch their head. It's a funny thing. We seem to have inherited it from a distant primate ancestor. Well, it's really none of the above. That's not the reason why we have 5 fingers. If you go back to the early land-breathing vertebrates, or air-breathing vertebrates, as they came out onto dry land, they often had more than 5 fingers. Some of the amphibians had up to 8 fingers, and yet that by reduction was simplified down by the time reptiles evolved. By the time reptiles evolved, they're all 5-toed. So reptiles evolved from a 5-toed amphibian, and that reduction, we'll see that this idea of reduction of complexity and evolution several times through the presentation today. Here you can see horses, one of the famous examples of evolution, and we can go back to ancestors of the horse that are 5-fingered down here. By the time you get to the modern horse, it has 1 toe. There are remnants of a couple of other toes up here, just almost like splints along the side of the bone there. And you can see in between there, you have 3-toed individuals. So evolution often reduces complexity, but we start with that 5 pattern because that's the basic pattern that was given by amphibians to reptiles, from reptiles to mammals, from mammals to primates, primates to humans. So here in the horse limb, you can see here in the forelimb, you can see in its embryonic development, even though it ends up with 1 toe, it has 5 in early embryonic development. And likewise with birds, it end up with 3 or 4 digits or toes. You can see in their early embryonic development over here on the right, the primordia anyway of a 4th and 5th finger or digit, if you will. So that, there's a saying that was very popular in the 19th century, that ontogeny, which is the development of the individual from a fertilized egg to an adult, that's ontogeny, recapitulates phylogeny, which is the history of the evolution of a group. And while that is taken with a grain of salt today, it was thought to be almost a universal law of development back in the middle of the 19th century. Now we understand it as a pattern that sometimes occurs, but certainly not always. But here we can see an early pattern of early vertebrates as they moved down into dry land, the 5-digit limb that later becomes simplified in later development. And when did all this happen? Well, modern amphibians with 5 digits start about 350 million years ago. So our 5 fingers date back to about 350 million years. From then we go from amphibians to reptiles to mammals, etc., all the way up to modern humans. But there's an even better question we can ask looking at this graph. It's the question that's been asked over and over and over again. Which came first, the chicken or the egg? So don't look at the graph. Which came first, the chicken or the egg? Okay, you got the answer in your head. Well, the egg comes first. The egg is about 300 million years old. That's the key to the evolution of reptiles, their ability to live on dry land without an aquatic life stage. The dry land egg is a semi-permeable membrane and shell that allows oxygen diffusion. So that's about 350 million years ago. And birds are much later, which chicken is a bird. So that's about 100 million years. So definitely the egg comes before the chicken. Now you know the answer to that question. And now we're going to talk about temperature regulation in animals. Thank you. Thank you. Yes, I'm of that generation. So we're going to talk about temperature regulation in animals. And it turns out that when you look at animals, we generate heat in our bodies. I mean, in the mass of our bodies. So a larger body generates more heat. But we lose heat to the environment across the surface of our bodies. So there are two different, we generate heat in the body, we lose it across the surface of the body to the environment. So the relationship of mass or our body size to the surface area is important to staying warm or staying alive, as the Bee Gees might say. So I invented three different animals. These animals all weigh the same. The one on top doesn't appear to because you're looking at its edge. That's a disc-shaped animal. That's our pancake animal. And we have a snaky animal down here, and then we have a chunky animal in the middle. So these are three different animals. And so here the diameter, we have a length surface area of 108 units. And the shape ratio is, I just say it's the long dimension divided by the short dimension. That's about 25. So an animal that's really strung out or a pancake shape has the short dimension is really very short. So it's it has a high shape ratio, what I'm calling here. And likewise with a snaky animal, it has a very long dimension and a short dimension. It ends up with a shape ratio that's very large, whereas a chunky animal has a very small shape ratio of only 2.5. So let's think about animals these shapes. Well, there actually are animals that are kind of these shapes. They don't look like cylinders, pancakes, but we'll look at them just a second here. So we have 6.9 units of surface area for every unit of mass. Down here 4, so around 7 and 4, but only 2 units of surface area for every unit of mass. So imagine that all these are warm-blooded animals living in a cold world. This one would have the hardest time keeping itself warm because it would be losing heat very rapidly for every sort of unit of energy or heat it could generate in its body. And this one would stay the warmest the most easily, a chunky animal, because it has a very low surface area for every unit of mass. And so we can look at animals, and I just quick took some measurements from pictures and came up with these sort of long divided by short ratios here. And you can see that all these warm-blooded animals, the ratios are relatively small, less than 5, between 2.5 and 5, even weasels that, you know, we think of as long as skinny, and people which actually end up with, at least for warm-blooded animals, very lanky ratio. Of course, we're actually a tropical animal. We really come from Africa. So had we evolved in the Arctic, we might be sort of shorter, chunkier animals. But you look over here at least a selection of cold-blooded or poikilothermic animals. Now, certainly you can find chunky warm-blooded or cold-blooded animals like turtles, but the point is that cold-blooded animals can occupy shapes like this green snake or a flounder or a ray, or I think there's a fox snake there. They can occupy shapes that would be completely impossible for a warm-blooded animal, because a warm-blooded animal can never keep itself warm at those shapes. It would have way too much surface area for its mass. A green snake would have to just be eating constantly to keep itself warm, or have dense fur over the snake, which would complicate the whole idea of being a snake. So some of the shapes you see of animals are really linked to their whole metabolism. I remember growing up in biology class. Of course, this is, you know, back in the late Pleistocene when I was in high school, but it was sort of treated like warm-blooded animals were just better, more highly evolved, and therefore sort of better and more advanced in an evolutionary sense than cold-blooded animals. And to some extent, warm-blooded animals are derived forms, so they are more advanced in that sense. But snakes are incredibly successful animals, very diverse, relatively recently evolved reptile. And they occupy a sort of niche in ecology and occupy a shape that allows them to exploit that niche. That's completely impossible for a warm-blooded animal. Bats would seem to be the warm-blooded animal that breaks the rule, don't they? I mean, this is not a paper membrane here. This is living skin. And so all of this is a surface across which heat is lost to the environment. You would think a little brown bat, which is just a little over 3 inches long and almost 10 inches wide, just so flat and pancake shaped, at least much of its body, that it would be an impossible shape for a warm-blooded animal. But bats have figured a way around it. They are warm-blooded, but they actually aren't like you and I. I mean, we have to maintain an almost constant body temperature. I mean, typically a person's body temperature drops maybe a degree or so at night when you go into deep sleep, which actually conserves quite a bit of heat, just that 1 degree temperature of body loss. But bats can drop their body temperature right down to the ambient temperature of whatever environment they're in. That dramatically reduces their heat loss. And they wake up in the morning and increase their metabolic rates 15-fold and their body temperature up to 100 to 106 degrees. And to support that high metabolic rate in this, at least from a terms of heat, from heat expenditure, a sort of metabolically wasteful shape, the bats have to eat their body weight in insects every night. Wouldn't I love to eat my body weight in pasta every day? So the bat is sort of the exception that proves the rule to this. When a warm-blooded animal occupies this risky shape, it has to have some very special metabolic adaptations to allow it to exist. Allen's law really deals with the same phenomena, which is the shape of animals. I mean, I remember reading about this in the early 1980s when I was in junior college, my very first ecology class after being out of college for a number of years. I came back and took this and I saw Allen's law in mine. And at that time, it really hadn't been tested very thoroughly. They have done some actual measurements and statistical tests of this to see if it's actually true as opposed to being an appealing idea. But this was always the classic example of the red fox, sort of long, lanky fox, and the Arctic fox, which is much more chunky in its shape. And that as animals migrated and then adapted to colder environments, the limbs became shorter, their body was more compact, really as a way of minimizing heat loss. So let's think now about just the mass, just the size of the creature and its surface area and how that might allow it to stay warm. So we're going to have a perfectly spherical animal that's 1 unit wide and one that's 2 units wide. Well, the surface area is related to the square. There's the radius. So we increase this linear measurement by 2, but we're going to square the radius to get the surface area. So the surface area goes from 3 to 12. The surface area, we double the linear dimension, we increase the surface area by 4. We increase the volume by the cube of that. So when we go from 1 to 2, now it's not just going from squaring that change. Now we cube it. And so the mass goes from 0.26 to 2.1. So we're 8 times the mass, 4 times the surface area and 8 times the mass. And so 12 units of surface area for every unit of mass for the tiny animal and only 6 for the big one. So even though it's exactly the same shape, when you double its size, it's twice as easy to stay warm because it has only half as much surface area for its mass. So there's an advantage just to being big in an Arctic environment, just to being big in order to stay warm. So this is why a gnat, 3/32 of an inch, and a hummingbird. I mean, a hummingbird is a very tiny bird, but could we make it even smaller? Could we reduce a hummingbird down to the size of a gnat, and then it could, well, we could exploit a whole new niche of working with very small flowers and ability to occupy a whole different ecological niche. But the ratio is 32 times is different. So the gnat has about 32 times more surface area in relation to its mass than does a hummingbird. And if you made a hummingbird the size of a gnat, it would instantly die of hypothermia. It couldn't maintain its body temperature, it would crash and it would die almost instantly. So even though the hummingbird is a very small bird and has to be hyperactive to maintain itself at that size, but if you tried to make it even smaller, it would just become physiologically impossible to eat enough fast enough to stay alive. Even at the size of a ruby-throated hummingbird, it has to eat about half of its body weight in bugs and nectar every day. And we can see this becomes Bergman's rule in ecology, that if you look at the same species over a wide geographical range from north to south, you can see that the animals tend to get bigger in the northern parts of its range. White-tailed deer, you go to the Upper Peninsula of Michigan or Montana, tend to be much bigger than white-tailed deer in Florida, and you can go into the Everglades deer that even get much smaller than 100 pounds. Because they're growing in a much warmer place, they can cool themselves much more easily at a small body size, and they don't have to keep themselves warm in the winter. Now we're going to talk about really about sizes and shapes from a different point of view. Now we're going to talk about the mobility and the movements of animals in relationship to their size. This is a wonderful book I read, oh gosh, now probably 35 years ago. I was still in college. J.B.S. Haldane was a mathematician and a evolutionary biologist living in India, British India, writing before the war. This is actually a group of essays he published in the Daily Worker. Now we're going to talk about getting big. Some of you know the movie this came from, which was called Big, and the little boy that just wanted to be big. But be careful what you wish for. Getting big changes a lot of things. You don't just get to be bigger. Let's look at a white rhino and a Thompson's gazelle. Just two animals. They're both quadrupeds. One is 100 times bigger than the other. 50 pounds versus 5,000 pounds for a white rhinoceros. The rhinoceros is only 2.5 times taller. So the bones of a rhinoceros need to be about 100 times as strong or 10 times as thick. The strength of a bone is proportional to its cross section, just as the muscular strength of the legs is proportional to the cross section of the muscle in the leg. And so in order to, the legs need to be about 10 times as thick in relation to the body size in order to support the rhinoceros. The reason the rhinoceros looks, not only is bulky, but looks bulky and has big, thick legs and has a sort of ponderous appearance is because it has to support that weight. You can't, a 5,000 pound gazelle would collapse on itself. Couldn't support itself. It has to become that thick, bulky looking shape in order to support itself. So if we move people to Jupiter and leave them there for thousands of years and they evolve to that gravity, the gravity on Jupiter, I'll talk about going to Mars. Let's go to Jupiter. The gravity is about 2.5 times as strong, which means if I was on Mars, I would weigh same mass. Mass and weight are different. Mass is the physical substance. Weight is what happens when gravity interacts with mass. And I would weigh 387 pounds. I would weigh 2.58 times as much. And to support that, my bones and muscles I would need to be 60% shorter and 60% wider and deeper. In other words, I'd have to be in much more compact shape in order to move around in the same way that I move around on Earth. The body shape you have evolved under the gravitational field of the Earth. Under a much stronger gravitational field, human beings would have been a very different shape. This is one of my favorites because I get to show a picture. This is, I'm sure you recognize Bob Beamon. Bob Beamon broke the world long jump record in the Mexico Olympics in 1968. And guess who was watching NBC Sports on that day. Would have been, I don't know what time of year that was. I would have been 16-year-old Tom Simpson watching the Olympics on NBC that day when he broke the world record by over a foot. So we're going to talk about Bob Beamon, but also about fleas, sort of jumpers of the insect world. We're going to compare the two. And the flea jumps an amazing distance for its size. And tiny animals like fleas are governed mostly by adhesive forces, which is why animals fly can walk on the ceiling, and by air resistance as they move. Whereas large animals like people or rhinos are governed mostly by gravity and inertia. Just it's that sheer mass that governs how we move and how fast we can move. So let's say, how far could I jump? I'm going to be Bob Beamon right now. How far could I jump if I were a flea? A flea, it turns out, can jump about 13 inches or about 139 times its body length. Whereas I, being Bob Beamon, can jump 29 feet or 348 inches, or only 4.8 times my body length. So it would seem like a flea, even though I'm the world's best jumper, human jumper, I can only jump 5 times my body length, or way outclassed by a flea. Wait a second. If I could shrink myself down to the size of a flea, what could I do? Well, I'd be 1/768th as long as a flea. So if I just scale that 29-foot jump down, well, I could only jump a half an inch, about 0.45 inches, and a flea could jump 113 inches. So I'm way outclassed by the flea. But wait a second, we'll get back to our scaling issues again. So I square 768. In the cross section of my muscles, I'm 1/590,000th as strong as I was as an adult human, but I only weigh 1/453 millionth as much. And so I'm actually 768 times as strong for my weight. So I'm a real little mighty mite. I'm scaled down to the size of a flea, and I'm incredibly strong. And because I'm much stronger, I can generate about 27.7 times the push. And I'd have to go through Newton's just pretty simple equations, force, mass, acceleration, in that to show you where I got that number. But I could push. The push I would get from my muscles would be about almost 28 times, which would mean I could jump 28 times as far, which means I could jump about 12.5 inches. And it turns out that my Bob Beamon self could jump about the same as a flea if I were scaled down to the size of the flea. And my point of going through this is that really talk about the capabilities of animals is really a matter of their scale. The incredible jumping ability of a flea is produced by the size of the flea. If you scale the flea up to the size of a person, and we'll not worry about why the flea would die instantly if you did that, but if you scale them up, they wouldn't be able to jump 139 times their body length. They'd probably only be able to jump about 5 times their body length, simply because you're scaling it up. They're becoming much heavier in relationship to their weight. And the amazing flea would be no better jumper than at least an Olympic athlete. I don't know, I found that fascinating. This was one of the things that J.B.S. Haldane went through in his book written in the 1930s. And indeed, when you look at the speed of animals in relationship to their length, and so that's what this is, velocity, maximum velocity in relationship to length, you see that animals all the way from single-celled animals all the way down here, all the way up to blue whales, are moving at about the same speed in relationship to their length. This is about scaling. And to go faster in general, animals scale themselves up. I mean, this obviously isn't true of every animal. It doesn't mean every animal at the given size can move the same. Obviously, some are much faster than others, but as you look across the entire animal world, you see that there's a great constancy of the scaling effect as you go from very, very tiny to very, very large. I promised you an answer to this question. If a whale had arms and legs, could it dunk a basketball? I was worried when I started to investigate this, but it turns out that whales did have arms and legs because whales are fairly recent mammals that move into the ocean. And only 43 million years ago, there was a whale named Phyomycetus that had arms and legs. And indeed, from the fossils of Phyomycetus, he was 3 meters long, which is about 10 feet. So standing on his hind legs, which might have been a little bit difficult for Phyomycetus, but we're stretching the truth there anyway. And he weighed 600 kilograms, which would be about 1,300 pounds. And by comparison, probably not many basketball fans out there, but a recently retired NBA player, National Basketball Association player, was named Shaquille O'Neal, who was 7'2" and weighed about 325 pounds, which did he walk in the room where you were standing, you would think he was a giant. And yet Phyomycetus is 10 feet tall and weighs about 1,300 pounds. So I think he could probably muscle Shaquille O'Neal away from the basket and dunk the basketball. So there's the answer to the question. I'm pretty sure that a whale could dunk a basketball if he had arms and legs. So if anyone stops you on the street and asks you that question, you've got an answer now. So let's look a little bit at the plant world. Again, looking at shapes and sizes and scaling of trees and why they look the way they look. They seem to occupy a number of different shapes. There's a giant sequoia, that's a sort of classic open grown oak tree. There's a conifer, I'm not sure of the dimensions, but you can see how the conifer sort of changes shape as it gets bigger. It seems to get fatter at the base as it gets bigger from the right to the left. Let's investigate shapes of trees and the stresses on the tree. So there are two things I want to talk about as we think about how a tree is shaped and the sort of stresses on the trunk of the tree. One of them is just compression. So as the tree gets bigger, it weighs more, and that weight would have a compressive force on the wood of the tree. And obviously, wood is pretty darn strong stuff, but you could eventually crush the wood if you just put more and more stress on it. And so the way there are two different shapes we might think about. We might think of trees as a cone, wider at the base, narrowing as you go up, but in a linear way. And so as you go up, it's just getting smaller and smaller and smaller in diameter. And if you do that, it turns out that the stress on the bottom in terms of weight per square unit, square inch, or square centimeter at the bottom stays the same. Doesn't matter how big you make the cone. You can make the tree bigger and bigger and bigger and bigger and bigger, and it will still be the same stress on the wood. So that's one answer to the question, that opposed to a cylinder. And as you make the cylinder longer and longer and longer, you make the stress on the base more and more and more. So it's one of the reasons why trees are not perfect cylinders from the top to the bottom, because it would be an unstable shape. We'd be putting more and more and more stress, compressive stress on the tree at its base, and it would eventually fail. But let's look at the other stress to think about as we're designing our trees. And this is the bending stress of wind. So as trees get taller and wider, the bending stress due to wind resistance is proportional to the increase in the crown surface area. It's a linear dimension to get the surface area, or the height is a linear dimension, the width is linear, the surface area is a square. And so as you make the tree twice as tall, it has 4 times the bending stress, 4 times the wind resistance. So 3 times as tall, 9 times the wind resistance, 9 times the stress on the trunk. So as you make a tree twice as tall, needs 8 times, so needs a trunk 2.83 larger in diameter. Again, it would be the square of 2.83 to get up to 8 times as strong. So if it's twice as tall, but has to be 2.83 times as large, we're increasing the diameter faster than we're increasing the height. With a cone, you're increasing them at the same scale. Now we have to increase the diameter at the base even more. So we end up with a shape like this. We end up with this concave cone shape for the tree we're designing here to be stable in the wind. That doesn't look much like a tree, does it? But it turns out that when you look at trees, the study done in the tropics, but looking at each one of these lines is a different species of tree, it turns out that when you look at trees, the diameter at the base is on the vertical axis. This is the height in meters from the ground. And see, it's not a straight line, so trees are not cone shaped. It's curved. And so as the tree gets bigger, it starts increasing in diameter faster and faster and faster. So the tree ends up looking, even though to your eye it doesn't look this way, it's scaling itself into that shape as it grows. And it does that less in a plantation where you plant the trees close together. Why? Because there's very little bending stress. There's very little wind stress on the tree in a plantation, other than a little bit at the very top, but the trees shelter each other, whereas an open grown oak is out in the wind and so suffers a great bending stress, and so takes on that really fat, generally buttress at the base shape, and gets narrower very fast as you go up to the very top. The tree is shaping itself to resist the bending stress. And this is my plant identification paradox. And this one, I want you to put because I'm going to ask you a question here in a minute, and I want you to put your answers in the chat, and then Jackie can take a look at your answers. So the plant ecologist, some of you may know our plant ecologist, but I will leave her anonymous here. I think she's actually on the call right now, so I got to be careful what I say. Plays a trick on me and asks me to identify a plant specimen. It's a sedge, but Lori already knows the answer. She's checked it out with a real expert, and she's just doing this to see if I can figure it out. And she gives me three possibilities: Carex aristotelius, Carex platoniensis, and Carex sacratoides. And I'm completely flummoxed, which is often the case when I work with a Carex. So I just pick Carex platoniensis because the name has a nice sound to it. I figure I got a 1 in 3 chance of being right. And then she reveals, because she knows the answer, and she reveals that it's not Carex aristotelius. Okay, so I picked platoniensis. Lori tells me it's not aristotelius. So should I stay with my first guess, or should I switch to sacratoides? Now I want you to put your answer in the chat. Stay or switch. I'll give you about another 10, 15 seconds here. So this is a tough one. I don't like to be wrong, so I want you to guess right here. Lori's always playing tricks on me, so should I stay? Should I just go with my gut, first guess, or should I switch to sacratoides?
We've got a couple of stays, a couple of switches, more stays, more switch, more stays. We're about 50-50 so
Okay.
far. One more switch, another stay. This is very exciting.
Okay. Well, I'll cut to the answer here, and the answer is you should switch. You should always switch. And the reason is that I had a 1 in 3 chance of being correct, obviously, when I first guessed platoniensis, right? What else could it be? And Lori, who already knows the answer, doesn't change the original odds because she knows the answer and can always pick a dud. Regardless of what I pick, she can pick one that isn't the answer and tell me that's not the answer. So that doesn't change my original odds. It's still 1 in 3, even after she reveals versatility. So I've still only got a 1 in 3 chance of getting it right. But it has to be one or the other. So I have to have a 2/3 chance of being right if I switch. And so I switch. And a lot of you, usually people, I know you people out there are really smart, but almost everyone, when they first hear this paradox, can't believe it. Now, what I want you to do is to get 3 glasses when you go home, like drinking glasses, put them upside down on the counter and put something under one of the glasses. And just play the game with yourself, play it with somebody else. Just do it for a while and you'll figure this out. Because logically, it's hard to figure out. So I want you to do that when you get home. So we're going to take just a couple minute intermission here, or we'll go for 5 minutes. We're 5 to 12. The second half's a bit shorter than the first half, so we'll just take a quick intermission here. Some busy ants crawling around.
So we'll say it's 10:55 right now. Come back at 11 a.m. If anybody has questions, you can stick them in the chat, or you can just unmute and ask. We'll sit here and answer questions too. But if you need to use the bathroom or whatever, go grab a beverage, you can do that. We had a couple of comments in the chat as we were going. I'll just share those with you, Tom. See, when they were talking about why do you have 5 fingers, Christine said, so we can do basic math with 10.
That's true. That's true. Our whole base 10 numbering system is I never thought of this before. Our whole base 10 numbering system goes back to a 5-digit amphibian. Just think about that. Wow, I never thought of it that way. That's pretty cool. Because if we could have, you can use any base for a numbering system. We just ended up with 10 because we had 10 fingers,
Mm-hmm. When you were talking about which came first, the chicken or the egg, Janet said, I'll have to share that information with my hens.
Yeah, the egg came first.
BT said, I've noted the size difference in great horned owls. They're considerably smaller in the Southwest US versus the Midwest.
Well, that would make sense. I mean, for warm-blooded animals, staying warm is just almost all of your energy loss in a day. You don't think about energy loss most of the time because you're not cold. We have climate controlled environments. But most of the food we eat every day goes just to keep us warm. It's just about staying warm, and so the ability to conserve energy is really critical. And so body size and surface area mass relationships are just so fundamental to the shapes and sizes of the living world and the plants and animals in it. That's what fascinates me about these, what sort of seemed like gee whiz science, but I was always fascinated with it just because it revealed so much about the world I experienced that is invisible until you start thinking about just the sizes of things and how the sizes and shapes and that work together to allow animals and plants to do what they do.
We had a couple of comments on the plant paradox. One was Mythbusters had a show talking about this.
Oh, sorry, I was spoiled. Okay.
Another person asked what's the name of that puzzle, and they said they thought it was the Monty Hall problem.
The Monty Hall paradox, so let's make a deal. The 3 doors. There's I don't know what they put behind the bung doors, but there was a brand new car behind one door, and then there was nothing behind other doors. And you would make a choice, and then Monty Hall would have his lovely assistant open one of the other doors because he knew which the real door was, and so he could always open up a bung door. And then he'd ask the contestant whether they wanted to switch, and the audience would be yelling, switch, stay, switch, stay, switch, stay. But, and I think this actually happened after the show, they worked out the paradox and realized that you should always switch. And this was, I think, first on a Canadian talk show. And they had PhDs from around the country writing in and saying, that's ridiculous, it's wrong, it can't be. And if you try to logically solve it, it's such a, I did the same thing. I'm the original doubting Thomas. I mean, I heard this paradox and I thought, this is wrong, I'm gonna prove it's wrong. Yeah, that's just the way I am. Then after a while, I realized I couldn't, and then I took out the 3 glasses or 3 somethings, and I started playing the game with myself, and I thought, oh, it's so simple. When you start playing the game, it's just so obviously simple, but the PhD mathematicians were trying to solve it mathematically, which you can, but if you just take the 3 glasses out or whatever, 3 anything, you start playing the game with yourself, it becomes obvious why it's true. It's a fun paradox. It's one of the most fun. I love things that puzzle your brain and trying to and almost deliberately steer your brain in the direction that you're not used to going. So
all right, and last comment before we move on. Shape, size, body surface area is also why babies are harder to keep warm.
Well, yeah, it's also that you're just very small. Very, that size difference means that they can have a really hard time controlling their body temperature in relationship to an adult. A 6 pound as opposed to, a 60-pound child is 10 times as large. A 120-pound adult is 20 times as large. So, and that makes a huge difference in their ability to generate heat inside their body versus how rapidly they lose it across their skin to the environment.
All right, I think we can carry on.
Okay, well, the first thing we're going to do here is have a little fireside chat, me and Franklin Roosevelt here. And we're going to talk about a phenomena called reduction, or making things smaller. This is a little about how science works. Talked about ecology as science, and how science works and what it tells us about the world, and maybe what it doesn't tell us about the world. So in the common way we use the word reduction, we talk about making smaller, but philosophical reduction, or in science, it's well, an example of it was our friend Plato, who postulated that all chairs are really sort of manifestations of a perfect form of a chair. There was a world of forms, and there was a perfect chair in that world, and all chairs you see in our world are imperfect copies of the form of a chair. And likewise with cats, we can have any number of cats. They're all different from one another, bigger and smaller, and different colors and shapes and ages and weights, and yet they're all, in a sense, imperfect copies of the ideal form of a cat. That was Plato's idea, and that was a matter of reduction. He was taking complexity of all these different cats all over the world, of different shapes and sizes and colors and breedings, and he was reducing them to an ideal cat. So we can take 3 individuals and reduce it to a single idea, or what we typically do today is to group them under the category cat. So the 3 individual cats, real cats, that began at some point in time and will die one day, and they're different. They could be living in different places. And then we can count them. And so we can reduce 3 cats all the way down to the digit 3. So this is an example of reduction. It's what we call philosophical reduction. I'm going to show you why this is important to science and how we think about the world. But I've taken 3 cats, maybe your cat if you have a cat, and I've made them into a digit. And I've added all 3 digits together, and now the 3 cats are the digit 3. No more cats, just the digit 3. So that's an example of philosophical reduction. And let's look at how reduction works, just looking at something that's familiar to many of us working in ecological restoration and working with plants, in particular the floristic quality analysis that is routinely used in judging. I just used this fairly recently in looking at changes in the flora of Glacial Park over the last, I think, 33 years. We had a study that was first started in 1986 and how the vegetation changed between then and 2019, when I did another survey and we used floristic quality assessment to judge certain aspects of that change. So when we do that, we take a land individual, which I talked about last time. It's a word I use. Glacial Park is not just a space. It is an actual piece of land that has a particular history. It was Northern Pump Farms. Before it was Glacial Park, it was a number of independent farms. Before that, it was a prairie oak savanna. Before that, we can go back farther and farther and farther. It was a conifer forest from about prior to around 10,000 years ago. And before that, it was covered with ice. I mean, there are just all sorts of different things. That's part of the history of that land individual. It becomes, in this case, we'll talk about a prairie. That land individual that we're talking about becomes a prairie. So we lose all that complexity of the individual and we put it in a category. We then reduce the vegetation, which is not only many different species, but many different abundances for each species, different shapes and sizes of plants, different ages. Some of them could have invaded yesterday. Some of them could have been there for 15,000 years. And we're going to reduce that to simply a list of species names. And so we reduce complexity down to a single dimension. The next step in floristic quality analysis is to replace the species with a numerical coefficient, a coefficient of conservatism. And so we replace the qualitative species, but I mean qualitative in the sense that an apple is different from an orange. There can be one apple and one orange, but they're qualitatively different. And we can have compass plant and little blue stem are very different plants that come from different plant families. They have different growth forms. They may grow in the same prairie. Little blue stem has relatively shallow, very fibrous roots. Compass plant has a very, very deep taproot. So there's many, many differences between them, but each of them has a coefficient of conservatism of 5. So in that sense, they're identical. We've reduced them to the same thing, the number 5. And then we take and we calculate, we're turning every species into a digit. We then we take that numeric array and we turn that into a single number for a mean conservation or mean coefficient of conservatism. We just take the average of all those digits. But that's a choice. I mean, there are many, many other mathematical ways to describe an array of numbers. We choose an average because that was the person who originated this, Gerald Wilhelm, back in the I think it was the 3rd edition of Plants of the Chicago region. Just use a simple arithmetic average. You could use a median, a mode, a variance, a standard deviation, a geometric mean. You could all use all different ways of summarizing an array of numbers, but we use an average here. We reduce the complexity of an array that has many other properties down to an average. So why do we do that? I mean, we've left the historical individual in its full complexity and history way back there, and we've reduced it to a simple number. Well, first of all, reduction in that sense, you probably have figured out reduction is central to the practice of science, of abstracting and reducing and quantifying. It allows us to control nature, either physically or intellectually. I mean, we're mostly talking about intellectual control and power now to take nature and take it apart and quantify it and put it into equations and calculate things up. And it's probably inseparable from human thought. I mean, probably in the way we think about the world and abstract it and work with it. And floristic quality assessment has been a powerful tool used by land managers now for 40 years. But at the same time, it is both a very powerful tool, but its power really comes from its power of reduction And what the reduction does is it's left everything else behind, other than this one aspect, what I call an aspect of that place, or not even the plant community, but the place, the historical place that you were visiting. It's an extremely reductive practice. So what have we learned? Well, each act of reduction leaves behind most of the complexity of the previous level. So we start off, in this case, it's just a beautiful meadow with some shrubbery and maybe some woods in the background. It comes with a reward. Every act of reduction comes with a reward, but with a risk. So one of the reasons I recently did my phenology orientation, and every time I go through that, every time I talk about plants or trees, I try to tell people that just knowing the name isn't the point. I know the reason we like to know the names is it gives us a certain intellectual power to recognize things, and it makes us feel good about that. It does me too. That was one of the reasons I wanted to know the names of things, the names of trees when I was younger. But in naming things, what I want people to do is, I'd have named that Spring Beauty. Now that you've named it Spring Beauty, that's the first step. The next step is to get down on your hands and knees and go look at it. And go get your magnifying glass out and look into the flower, look at the stamens and look at the pistil, look at the shapes and look at the sepals and touch it. And then see how each one of the plants there, and it generally occur in little groups, each one of them is different from the other. So each one of these is a real world historical individual that is both part of it. It falls into a category and has a name, but it also has an individuality that makes it different from everything else really in the population, and for that matter in the rest of the universe. And so the phrase I've come to use is always in science and ecology to stay close to the phenomena. That I do mathematical analysis. Anyone who's watched me give a phenology presentation can watch me doing mathematical analysis, but the mathematical analysis is, and yes, I know it says Simpson's index on the screen, but that's not me. That's another more famous Simpson who invented the Simpson Diversity Index. Is that when I take a real world, a real place with a history and a soil and a hydrology and vegetation and animals that wander through, and I reduce it to a number, a diversity index, the next thing I need to do always in science is reintegrate, go back and ask myself, well, what does it tell me about this place? And not lose the place in the calculation. It's often, I find that's a habit in science that I find my fellow scientists, people that are much better scientists than me, seem to lose track of the real world phenomena when they're doing science. When you calculate an index, any index, to then take it back to the world and ask yourself, what does it tell me about the real world? What does it tell me about this actual place, this stream, this prairie, this forest? So I use an excuse to use the word behooves. It behooves us to take our newfound bit of knowledge and return to the tangible real world individual in its full history and complexity, and then ask ourselves how this knowledge fits what it tells us, and how does it help to broaden and deepen our understanding of that real world individual. That to me is the point of science, in ecology anyway, and conservation, is to always take it back to the real world. Being big and small. This is a fun one here. This is time to squirm in your seat. This is the smallest living thing known that's really capable of independent growth and reproduction, as far as we know. And this lives in primate, that means you and I, bladder, waste disposal organs, genitals, and respiratory tracts. So yes, you should be squirming in your seat right now. These little guys are all inside of you. And this is the smallest bacteria that they've been able to find, around a micron. I made a mistake talking to Jackie yesterday, so I have to always come clean when I make a mistake. A micron is a nanometer is a billionth of a meter. billionth of a meter. And so that makes this genitalium about 2 million times smaller than an amoeba, at least some amoebas. We'll come back to the amoeba later on in our presentation. That is a pretty amazing animal. So it makes it about 2 million times smaller than an amoeba. So that's as small, as far as we know, that's about as small as you can get and still be alive, be capable of reproducing yourself. Vaccines get even smaller, but they're sort of the quasi-living things. If you define a living thing as something it can reproduce, vaccines don't really reproduce. What they do is they inject, they attack living cells, inject genetic material into the living cells, take over the living cells, who then produce more viruses. And so they're sort of a hybrid between a mineral crystal and a living thing, and they force you or I or any living organism to produce more of themselves. So if any of you had COVID over the last few years, your body was creating the coronavirus and spreading until your body finally developed some antibodies to heal yourself later on. So viruses are even smaller, but let's talk about getting big now. I mean, animals and plants get very big, but we don't have any animals and plants the size, say, of the state of Texas. There are certain limitations on the size of plants and animals. We don't have them any smaller than that tiny little bacterium. But let's look at trees. Get up to about 300 feet tall and about 1,280,000 pounds. The blue whale is the largest animal who's ever lived, much larger than dinosaurs. And that's about 100 feet long and 400,000 pounds. So I was kind of surprised. I mean, the giant sequoia is 3 times as long and about 3 times as heavy, but somehow I thought a tree, maybe some big, heavy wooden thing, would be many, many times the size of the largest animal. It's only about 3 times the size of a large whale. And because I'm a big fan of Moby Dick, I had to put the sperm whale in here. The largest sperm whale I think they have around today is about 60 feet long. Probably in the past, they know they got at least 78 to 80 feet long and about 300,000 pounds. So maybe up to about 3/4 the size of a blue whale. And Moby Dick probably was a lot larger than that, if you believe Melville, which I always do. So, but that's about as big as you can get and be an animal. Interesting, they're warm-blooded animals at that size. Very easy to keep yourself warm at that size because of the sheer bulk of the animal. They don't, even though they live in Arctic waters, they don't need a lot of fur because they're just huge in size and can maintain a lot of heat inside of that big body. But the other way to get big is just to multiply the same functional unit. So an aspen clone, like the Pando clone in Fish Lake National Forest, it's 100 acres in size, 47,000 stems, and could be, we don't really know because there's no individual part of this that's 80,000 years old or even 1,000,000 years old. And 1,000,000 is probably just a guess, but the point is, there's nothing about this organism that gets old. I mean, the stems get old and fall over, but the organism remains below ground, keeps growing and sending up more stems. So it could be essentially as old as the soil that it's in. In most cases, something would have happened, climate change or something along the way that would have killed it. But in this case, they're guessing it could be up to 1,000,000 years old and 100 acres in size. So that's a huge organism. Sargassum seaweed can have strands up to 5 miles long. This occurs in the sort of doldrums of the tropics where there isn't a lot of movement of the water. And so those strands of seaweed can get longer and longer and longer. And another candidate for the largest organism is the honey fungus, genus of Armillaria. And that's over 3.4 miles. I assume this from some genetic analysis, they can figure this out. So you and I would walk in the woods, we would see this big clump here growing It looks like an old rotting log, and we'd say that is like one, and we might even say that's one mushroom, like one fungus there, or we might be a little more enlightened and say this is all one sort of fungal organism with all these, but no, this is just one tiny, tiny, tiny outcropping of an organism that's 3.4 miles across. And how can organisms do that? And they do that by repeating the same functional unit over and over and over again. And they do that so that they can beat the scaling problem. You can only scale a human being up so far before a human being can't support his own weight. And to beat this, so plants in particular can beat that problem by just growing and making more functional units all attached to the same original plant body. And so you get bigger and bigger and bigger by just repeating more and more of the units. And along the way, you can actually accumulate, because each time you grow a rhizome or root out there, there can be a somatic mutation in that root. And so that doesn't mean the population is identical. In fact, they can study genetic variation throughout one of those giant aspen clones and see that it's actually lots and lots of different genetic individuals. This is lots and lots of different fungal sort of genetic individuals all attached to the same organism. So this sort of makes us wonder about exactly what is a individual organism. I mean, are these individuals, or are they? I mean, I don't know. In this case, this is a conifer, so it's unlikely that they would be growing off a common root system. So probably those are two genetic individuals, or at least two, what we would call two individual trees. But we've got to be careful, because trees, it turns out, as they grow, can accumulate. This is very old trees, but we have oaks that are well over 200 years old, can accumulate up to 10,000 somatic mutations in their body. So the next time you look at a big oak tree in a field and you think of that as one tree, well, it is. Physiologically, it's one tree, but genetically, it's really not, because there can be many, many different genetic individuals when you get out to the level of the twigs at the edge of the crown, because there's been so many expansions of shoots in the history. In fact, if it's 200 years old, there's been at least 200 opportunities as it's set about, and then a shoot expanded out for mutations to occur, actually much more than that. And each time the mutation occurs, as that shoot grows out, it's carried throughout the branch as it goes farther and farther out and accumulates more and more mutations. And the flowers occur at the tip of the branch. So the flowers and the pollen or eggs that are produced, and eventually the seed that's produced out at the edges of the crown will carry all the mutations that have occurred since the tree began to grow. That's fundamentally different than animals. With you or I, when we were an embryo in our mother's womb, the cells that would become the sex organs in our bodies, those cells were sequestered very early in embryonic development. So it wouldn't matter if there were some somatic mutations as my arms and legs continued to grow and develop, because those had no influence on the germ cells that I would then pass on to my offspring. Trees and plants are totally different. The flowers, the reproductive organisms, are at the edge of the crowns of a big tree, and so they accumulate mutations. With animals, very, very little accumulation of mutations in the growth of the animal, because those cells are sequestered early in growth. Plants, on the other hand, in particular trees, carry all of those mutations. This is just a gee whiz diagram of a tree where they tried to map out the mutations on a tree. And so this is actually a question I used to wonder about. I used to wonder, insects have such short generation times. You learn about evolution and adaptation. Why wouldn't they would seem to evolve so much faster than oak trees. Why wouldn't you have so much why wouldn't they just eat up? I mean, trees, really old trees would just not exist. Trees would have to be very short-lived because they just couldn't evolve fast enough to stay ahead of the insect herbivores. But that's not really true because the tree isn't one genetic individual. It's a colony of ever-changing genetic individuals. And so in a sense, evolution is happening in the lifespan of the tree. Really true, because as the branches are growing out and mutating and changing, ones that are perhaps just have faster growth rates, or the leaves on that branch photosynthesize better, will then grow and develop at the expense of a nearby branch that doesn't have that same mutation. So the tree is a sort of evolutionary experiment all inside of itself. It's I love trees. Now I've learned something even more amazing about trees and why trees really dominate so much of the earth, for the vegetation of the earth. Food chains, okay? And I'm not talking about these kinds of food chains that used to keep me alive before I got married, but these kinds of food chains. So with nutrients moving through a food chain, it makes kind of sense that the grasshopper eats the grass, the frog eats the grasshopper, the snake eats the frog, and the eagle eats the snake. And the nutrients, the matter, the material elements go up through that food chain. Some of it with the animals is deposited in feces along the way, that then is decomposed. All that goes back and is picked up by plants again. So you have that cycle of nutrients. We always talk about cycles in nature. Here's a nice cycle, not all of that cycle, because some of those nutrients might then wash into the river, which then goes into the ocean, and that would be trapped in ocean sediments that wouldn't be released again until those sediments were uplifted above the ocean, and then the land worn down and plants grew in there again and made those nutrients go back into an ecological system again. But in any sense, nutrients cycle in a system, whereas energy moves through a system. Energy comes in as sunlight, and while we don't think of grass as warm, it is constantly burning up. Most of the sugars that it makes are then burned up to fuel its own metabolism. That heat energy goes back into the universe. The grasshopper, most of the energy it consumes in the grass goes back out of the universe as heat. Likewise, as frog, snake, and eagle, that heat that originally came in as sunlight is going back into the universe. What continues to be trapped in the bodies that then may eventually die and rot away, that chemical energy is then released by decomposers and goes back into the universe. So energy moves through an ecosystem. It moves in as sunlight and it moves out as heat. It's a through flow. There's no cycling of energy. There is storage in the body of a living thing, but there's no cycling of energy within the ecosystem, which is why ecosystems have this. When we look at energy use in an ecosystem, we see it forms a pyramid. Lots of energy is trapped in the producer layer. Most of that is lost as heat. And so there's relatively only about 1/10 as much left to be used by the rabbits. Most of the rabbits' energy goes off into the universe. There's only about 1/10 of that that's left to feed. Well, this is not a very realistic. These look like small snakes eating rabbits, but you get the picture. These could be grasshoppers here that are then eaten by the snakes. Most of that energy is lost as heat. Only 10% of that or less is available to that next higher level consumer. So you can't, this pyramid has a top, and that you can't have, if this is an eagle, we don't have enough energy left at that level to have a specialist eagle eating creature. That's why there are no eagle eaters and specialists that are wolf eaters and eagle eaters, because there just isn't enough energy left at that point of this trophic pyramid, called the trophic pyramid, to support another level. Energy comes in at the base, it's lost as heat, and the energy available at each level gets less and less and less and less. And this really is why you can drink the water from Lake Michigan, but why you're supposed to be careful about eating particularly large fish like salmon from Lake Michigan, and at least discipline how many you eat in a year. because things like PCBs and lead get into the zooplankton here at the base, at something like the concentration of the ambient concentration in the water, really very low concentration. But that zooplankton is eaten by very small fish. So all of those toxins are taken in to the fish, but fish, like all the rest of us, didn't evolve in a world where there were PCBs. The organisms didn't evolve into a world with PCBs and lead because that just wasn't a part of the natural environment. And so we don't have any ways to excrete them. And so they build up in the flesh. And so they build up in the flesh. Most of the energy, the chemical energy of the zooplankton goes off as heat, but the toxin is left. And so all that toxin is then transferred to the next and it becomes even more concentrated. You see the concentrations going up here by about a factor of 10 as we go between these levels. So even though I can drink the water of Lake Michigan, by the time I get up to a really big fish, the toxins have gotten concentrated enough that I really shouldn't eat it. And again, if I eat the fish, it means that those toxins are trapped in my body. I can't get rid of them. So it's not just eating one fish, but more fish after that and more fish after that. The toxin concentrations in my body get more and more and eventually reach levels that can cause cancer. So just quick review. Energy comes into the sun, moves out back into the universe as heat. Nutrients can be cycled within an ecosystem. Energy comes in as visible light and leaves as heat. Complex, so let's fit the organism into this. The complex organized structure of plants and animals grows out of more simple, relatively unorganized materials from the environment, and then degrades back into the simple materials again, right? So I'm made up of carrots and hamburgers and pasta, and eventually, like all of us, I'll grow and die or live and die, and that all of those material parts of me will then eventually go back to be degraded into simple mineral components, and then hopefully, I hope, made available to plants at some point in the future. I know the way we bury people now, it may take a million years, but eventually. This transformation to simple complex is powered by sunlight, visible light energy that's transformed to heat. So that we're going to talk a little bit next about that miraculous transformation from simple things to complex things. And this is where we get just what I entitle It's a Messy World. If living things are so wonderfully complex, and they are, they're the most complex things we can imagine that we've ever found, complexly organized things. It's just incredible, down to the level of molecules in the DNA molecule, all the way up to the tissues and organs of large animals, just incredibly complicated things that are built out of simple mineral constituents. And that's a pretty miraculous, or what seemingly miraculous transformation. And one might be tempted to think there must be some sort of innate tendency of the universe to do that things go from simple to complex. Well, let's think about it. So we have here just a human egg that goes from an embryo to a baby to an adult. I mean, that's a pretty amazing transformation, right? That's a pretty amazing transformation from simple to complex. But let's look at the whole thing that's happening here, because this is only looking at part of the system, right? I mean, this is an amazing part of the system, but we take all the hot dogs and French fries and soft drinks, which are all, well, the soft drink, not so much, that's mostly just sugar water, but certainly hot dogs and French fries and everything else that you eat is complex organic tissue. They're all living things. You're gobbling up living things constantly that we have to. We're animals. That's what we eat. We don't often recognize them as living things when we buy them in the grocery stores in cans and saran wrap and sitting on styrofoam trays, but they're all living things. Carrots are just as alive, or were just as alive as you and I. We have to eat those very complicated, highly organized living things to stay alive. And out of this, we grow this, in this case, beautiful, human body, this incredibly complex, organized human body. But we also create a lifetime of think about it, urine and feces and heat that's pouring off of our bodies all the time. So we think of the mountain of all the food you've ever eaten in your life. For some of us, and did a big pile of it. And that's a pile of living things. That's a pile of life over there that you've consumed and degraded into waste products in order to build your body. And then you have produced your own pile of waste and heat energy on the other side. And so this, what seems like a miraculous transformation is miraculous in many ways. I mean, life is miraculous. I think that every time I look at a flower in a magnifying glass, the miraculous sort of complexity and beauty of life, when you look at it from an organizational point of view, you see that, well, it's not quite so miraculous. I mean, we're going, yes, this is simple, but we're really going from an incredible pile of complexity to an incredible pile of waste over here, and this one beautiful, complicated thing. So that in that sort of thinking about the order of nature, that's maybe a little bit less miraculous than we thought. And this is where we think a little bit about what physicists call entropy. This is a concept that we came about in studying steam engines in the end of the 19th century. They came up with this idea of entropy, and it's really about the order of things. We can see pretty clearly here that this seems more ordered, right? Entropy is the degree of disorder or randomness, and this seems much less randomly ordered, right? If we started with this on a tray and we started to shake the tray, we would probably have to shake it a long time before it ever did that, and we might die before they ever just by chance went together like that, right? I mean, it's just that whereas we could start with a tray of this and shake it for a while and come up with a disordered array pretty quickly, right? So it's the natural tendency in the universe to go from order to disorder, not the other way. As we were suggesting before, that we would start off with simple constituents and build this marvelously organized human body. So in the universe, this principle of increasing entropy is with a universal law called the second law of thermodynamics, going from low to high entropy, going from high order to low order. There's your Excel and hot dogs going to the person and the lifetime of waste products and heat. Well, let's scale it up now. Let's think about nature, that human landscapes tend to look more like that, right? My neighborhood reminds me of this. Frankly, a little bit boring, front yards and a yew hedge there, and a blue spruce tree in the front yard, and a privet hedge. It's pretty boring. And they're arranged sort of rectilinear organizations often. Whereas nature, when I walk in a prairie, reminds me more of this sort of wild scattering of plants of different kinds, mixed and matched all around through nature. And so let's think about two prairies. This might look like a prairie, but we're going to imagine that this is a prairie garden, and the species are all arranged in squares and rows, and we have 100 species of plants there. It's maybe not a prairie we're used to looking at, because we're used to looking at a prairie like this, the same 100 species, all more or less randomly scattered and mixed around within themselves. These are two radically different prairies. If we took this prairie and waited 5,000 years, we probably, if we could live that long and watch it, probably it would never move through any phase that looked like that, right? Probably we would have to wait even billions of years. It would never by chance organize itself into that. But if we took this prairie where all the plants were in rows and squares, and we made it 5,000 years or 10,000 or whatever, eventually those plants would just sort of mix and match and move around, and we would have something that looked maybe a little bit like this. So we're going, which one is more ordered? I think pretty clearly this is the one that looks like that, nice, neatly organized array, and the prairie looks like this more dispersed array over here. So the more ordered one is on the left, which means that we're going from this low entropy, very highly ordered system to a very high entropy disordered system, which it means that nature, despite the fact that we and we're just mesmerized by the beauty of nature. And you walk through a prairie, particularly an old remnant prairie, and you look down and it's just incredible. And every time you get a little bit closer, you get on your hands and knees and you see more diversity. It's just amazing complexity and beauty of nature. We don't like to think of that as a disordered arrangement, as a random scatter, but it comes much closer to that than does the garden in your front yard. And so over time, these highly ordered arrangements, if you had ever gone back and rearranged this prairie into this, given another millennium or 2 or 3 or 4 or 5, it would have changed back into this disordered arrangement. So let's think a little bit about change in nature and think about this principle of organization and spontaneous change in that organization. We're going to go back in a helicopter, my helicopter time machine. Each year in my budget request to Ed Collins, my manager, is a time machine. And he finally gave me one. And I went back with my bulldozer in the time, it was a big time machine. And I bulldozed. I'm a pretty nasty person. I took this beautiful prairie and I bulldozed an acre of ground in it. And then I left. But in my time machine, I kept looking at, I could look at this thing as it changed over time. And what I found is that the prairie from all around that brown patch was invading it from all sides and slowly making it look more and more like a prairie again. And then eventually the brown patch disappears and it looks like the prairie around it. Okay. So we go from a highly disordered state. We've actually introduced order. I've introduced a contrast with a bulldozer. We don't like to think about that, but I've actually created a more highly ordered arrangement with a bulldozer than the pristine prairie. I introduced a contrast. Over time, the contrast starts to disappear until I get back to that disordered prairie-like arrangement again. And this is important because it's a way of thinking about the modern era. That prairie now looks like this, right? City or farm fields or towns or whatever. That prairie now, let's say we've now got just an acre left. Just an acre left of that formerly 10,000 or 20,000 or 500,000 acre prairie. All that's left is that 1 acre, and it's surrounded by a hostile alien world. And so that hostile alien world is slowly pouring into the prairie. This change isn't any different than the first case I talked about. This is the sort of change that's been going on in prairies and oak woods back to the time of the glacier, and before that to the beginning of terrestrial vegetation. This is how things change as the outside moves to the inside. Any sort of contrast is blurred and covered up as plants migrate across the contrast to equalize the sort of potential for change on both sides of the boundary. So influx of weeds until eventually our natural areas would look pretty much like the city in terms of the plants and animals in them, because they would just be overtaken by those what we call weeds. Until eventually the natural area would, for all practical purposes, disappear. And this has great importance for us as managers today, because it means that natural areas today will never, don't have any tendency whatsoever to return to their predetermined past. No, there's nothing about an area of ground that has a memory and wants to go back. It's transformed by the world around it. And to maintain a natural area requires intentional human effort. It requires ecological restoration. That's why we do ecological restoration. The spontaneous nature sitting in a human world today spontaneously falls apart and turns into a disturbed human landscape around it. And in order to counter that, we need to do ecological restoration And that happens only when you and I and other people like us really address that what I see as the moral duty to conserve the beauty and diversity of life. That's why we do it. And there's never any finishing the task until you essentially created all of McHenry County was covered in the same plants and animals as you want to have inside of your prairie, which means that restoration is a task that can never be finished. It's a living relationship between people and land. I mean, that's the sort of moral conclusion from a very scientific line of reasoning. For to me, this is why these ideas of entropy and change and spontaneity of change are so important in understanding how we exist in the world today. I'm going to go through this and then we'll go right to the end here. This is evolutionary progress, really talking about exactly what we've been talking about today, this idea of progress that from bacteria to chimpanzees, who incidentally are higher on the primate evolutionary scale than we are. They actually branched off of the primate line after the line that became modern humans. So at least in that one way, you could say they're more advanced than we are, even though we like to think of ourselves as the pinnacle of evolutionary progress. Surely that couldn't be an accident going from bacteria to chimpanzees. Or could it be the result of innumerable changes, each change random with respect to complexity? So let's just look at a practical, I actually thought this one up. So let's think about perfume in a room, all in the bottle. So I've got the stopper in the bottle. I know right where the molecules are. And the second before I take it off, I know where all the molecules are. They're right inside the bottle. But 5 seconds later, they start to escape. So my knowledge of where the perfume is becomes less and less certain. The molecules start to scatter completely randomly. The molecules are moving in random directions until eventually they more or less fill the room and are randomly scattered all throughout the room. Well, let's think about it from the standpoint of smell. Before I open the bottle, I can't smell it. I'm standing right over here. I can't smell it. But as I open the bottle, the wave, what I should call the smell, when the first molecules meet my nose, starts to move in a regular path across the room. So I can get a very directional progressive movement out of a lot of random movements. So randomness and directional movement can go together in change. And so when we can take all those random movements and actually create a directional progressive movement. So the answer to the question, could that have happened? And the answer is, well, and maybe. We don't actually know. I mean, I'm not doubting that there many times is an advantage to more complexity, but we'll see that that's really not always the case, because let's consider the possum, the lovely possum. The possum is not fast, it's not strong, it's not big, it's not ferocious, and it's not intellectually gifted, but it's incredibly successful. It continues to spread, moving northward in the United States. Its population is increasing. In this case, simplicity, or at least relatively so, to the placental mammals with much larger brains, seems to be just fine. And it seems to, we could imagine maybe a really smart possum would be better, but possums seem to do very well with a very, very relatively primitive mammalian pattern. And look at the duckweed. This is a highly evolved organism. It evolved from things that looked like Jack in the Pulpit and arum that evolved into a duckweed. So evolution can actually move in the opposite direction, from complicated, big, beautiful, complicated things to the most simple, rudimentary life forms like a duckweed. I'm going to move through this one because I was all good, but I want to just get to the best part of the presentation, which is to take all we've learned about animals and plants and how they change and move, and their sizes, their metabolisms, and whether they keep being big and staying warm. And we're going to consider movie monsters and let's get real. Let's consider exactly how realistic are some of these movie monsters that we've been watching since childhood. So, Godzilla. Why is Godzilla impossible? Okay. you think about it for just a second. Think about what we've talked about so far. Why is Godzilla impossible? Well, what would he eat? I mean, look at the dentition there, all those sharp teeth. He's not a plant eater. He has to eat flesh. That's a pretty big body to support. So what is Godzilla going to eat? It seems to me implausible that you could ever get a predator that large unless there were other giant animals to eat and lots of them. So I think that's a bit implausible. He's too big. The scaling problem is going to be a problem with a lot of these monsters. They're too big to stand up, much less knock over buildings. And the atomic fire breathing, really no evolutionary precedent. There was a whole range of monster movies that came out in the 50s and early 60s that were all about radiation because it was so new, in particular from Japan, that had been the victim of nuclear attack. I mean, at the end of World War II, we felt it was necessary to drop nuclear weapons on Japan. And so they had a personal experience of it and a personal fear and paranoia about radiation. So some of these early radiation-related monster movies about radiation causing little lizards to grow into giant fire or nuclear fire-breathing creatures came from Japan. So let's consider his nemesis in that previous one, King Kong, one of my favorite movie monsters. I mean, who could watch King Kong without crying in the last scenes of the movie? And who could not be rooting for King Kong when he was fighting with the airplanes? But is King Kong real? I mean, come on. We have the omnivorous. Well, he is omnivorous. This is a plus there because gorillas are omnivorous. So we can imagine him eating an orange plantation or maybe a cornfield, just sort of grabbing whole big wads of it and eating that. So there's at least some plausibility to the fact that he's omnivorous and to feed himself. But the scaling problem again is just, a gorilla of that size couldn't stand up. So this is a problem with a lot of our movie monsters. This is one of my favorite movie monsters. I've actually watched this movie when I was young, The Blob. If you haven't seen it, I don't know where you can get it now. Whether exactly, I'm not sure. I don't think Netflix has it. So maybe the library would have it. But look at this. This is a wonderful monster. It looks like a giant sort of plastic sack full of pomegranate seeds. Here it is a sort of smaller, cute size, but it eats things. It eats you alive, and so as it eats, it gets bigger and bigger and bigger. And the great thing about this movie is that Steve McQueen was his first movie appearance, and he was the teenager who was desperately trying to warn the people in the town about the blob, that the blob was coming, but they wouldn't believe him. And so the blob ended up eating quite a few people. But there are problems with a blob as a monster, okay? I mean, he's obviously styled after an amoeba. I mean, a lot of monsters in the early days of monster movies were styled after something small made very large, and the blob would eat things by just sort of inhaling them, just sort of swallowing them up in that big red gooey mass. First, he has no excretory organs. He doesn't have a mouth, his skin. Skin is necessary with larger organisms to regulate the movement of gases and other exchanges with the world around them. He doesn't obviously have a circulatory system or respiratory. It's one thing in an amoeba size, you can have things diffuse from the outside to the inside, but with the blob, particularly this size, he looks about the size of a car here. So all the oxygen would have to diffuse across that membrane on the outside and move all the way to cells on the inside of it. Not very likely. So the blob, not very plausible as a movie monster. Oh, I remember seeing this movie too with them. Check this out. No conspicuous gender roles here. The woman is in a skirt and has her Sunday hat on. I guess you couldn't go out in public without that. And the giant ant is attacking. Doesn't that helicopter look like it's smiling to you? Anyway, how about a giant insect? Well, there's very little food for such a large ant. It would have to be like some super, super big giants on the other side of the hill having a picnic with giant pieces of fried chicken on the ground to feed an ant like that. So that one doesn't seem very likely. At that size, he would snap his own legs. And the respiratory system on insects really doesn't work that way. It has pores on the outside called spiracles and trachea that are tubes that are just allow air to diffuse through the system and keep oxygen coming to the living cells on the inside. That works fine at insect-sized creatures. But in something the size of a bus, there's no way it could get oxygen to the cells on the inside. So that one really wouldn't work. Another of my favorite movie monsters, Audrey the leaf. That's pretty realistic, I think. Audrey, look at a pitcher plant. They look like they could be brother and sister. And look at the teeth and the teeth along the edge of a Venus flytrap leaf. Again, that's pretty realistic. And if we look at is that a scene from Little Shop of Horrors or what? Okay, so Audrey, I think, is actually pretty realistic. Haven't met that yet. So in summary here, I think Audrey takes the cake. Audrey is by far the most realistic, a talking plant, and I think I like, because I love botany. I think she really turns the table on the animal world, and that I like that idea. King Kong, omnivorous. I mean, I love King Kong, misunderstood, loving, and lovable creature. I mean, yeah, his love affair with Fay Ray was amazing, but the scaling issue is just too rough. The gorillas that large just couldn't work. Godzilla was never my favorite. Sort of a Tyrannosaur Redux, you know, but interestingly, they gave him larger arms, and so that he could knock things over, or that, you know, that's King Kong there. And you can see that they have to give him big arms because you can't knock buildings over with those little Tyrannosaur arms. And I think he really channels our childlike desire to break things. If you ever had children, you know how much they delight that you make the stack of blocks and then they come over and knock it down and they just scream with delight and laughter, and you build it up again and they knock it over again. I think Godzilla really channels that part of our inner self. The giant ant is omnivorous, so that's a positive. And he's the hardworking little guy grown up, but the scaling issue again difficult. And the blob, well, yes, the blob gave us Steve McQueen, and that's something important. Really not very. We scaled an amoeba up to the size of a truck, and it really doesn't work anymore. So there you are. That's using what we've learned about plants and animals to talk about movies. Thank you.
I've got a couple of comments in the chat we can share. So first of all, this is fantastic. Love the combination of biology, math, and physics. And there was also a question/discussion. I've been told that it's better to cluster same species of flowers together so they're easier to find for pollinators. Nature may indicate otherwise. Do you have any thoughts on this?
Well, when I said nature was randomly organized, it's not. It's hard to find randomness you can create with a sort of mechanical device, but you can't really create randomness in nature because historically, any population starts in one place and seed dispersal moves plants to another place. So a completely random arrangement isn't really possible, and you'll always find that populations of plants tend to be clumped here and there. And for that matter, a field, you know, the size of that field I was showing, let's call that 20 acres, is not homogeneous. There are wet spots, dry spots, and maybe sandy spots. So they're always going to be heterogeneity in a field like this. My point is only that it approaches randomness to a much higher degree than your garden. You intentionally create order in a garden. We human beings like to surround ourselves with order in the house, order in the garden. The idea, yes, we do have some native plant gardens, and I hope those become more common. But even those, in order to fit into the neighborhood, really can't be completely wild, crazy, 6 foot tall plants flopping over the sidewalk kind of thing. So we have to maintain order in the landscape around us. And relative to that, nature is disordered in its arrangement. So it's really just a contrast between the two.
Just for the record, if anybody has to go once it gets to noon, you're welcome to. Tom and I will stay on and answer questions. We're getting messages in the chat, so I'll just keep reading them until we have no more. So we had a comment, I've never seen the movies, but maybe I'll have to now with this new knowledge.
Yeah.
Also, The Blob is on HBO Max.
Oh, great. Well, I'll have to suggest that to Sarah, my wife, one of our evening things, an old monster movie. I love to watch. They were so corny, they were good, and the monsters were the special effects were so clumsy that they were good, and yeah, it's the problem with special effects now is they make things so realistic that, I watch the old movies and Godzilla knocking over buildings it's wonderful. So I encourage you to go back and watch those movies. But when you watch them now, you have to start thinking about the realism of that and how real plants and animals work and move and keep themselves warm and all that.
Lots of love. The sense of humor is terrific. Very wonderful, and thank yous. Question: why were there giant dragonflies millions of years ago, but not today?
Well, you can continue to modify. It's a good question because you can continue to modify. Now you could, in theory, we have about 20% oxygen in the atmosphere now. You could, or evolution, if we could get rid of all the birds and other creatures, it might be possible to evolve larger insects in the world today. Simply by creating a more extensive tracheal system and more or larger or more spiracles to allow more diffusion of gases through the creature, you could exaggerate that system and maybe make them larger. But one of the reasons why they could be larger in the past is because oxygen contents were much higher in the atmosphere at certain times, and that allowed animals that were dependent on oxygen contents to be higher. So it's to be larger. So there's both of those things, but probably the most important one is that we have a world full of other creatures that occupy those larger sizes that simply don't leave any space for giant insects that either mammals or birds or lizards or amphibians can occupy those spaces more efficiently. And you really don't leave those spaces for giant insects, beetles the size of wolves or something I don't know. I'm not an entomologist, but you might be able to have a beetle. You can have beetles up to this big. I mean, there are beetles in the world, so they might be able to evolve up to the size of a wolf, but the wolves are already there, and so that sort of ecological niche isn't available to a wolf-sized beetle.
Comment: if mosquitoes were huge, at least we'd see them coming.
Yeah, I saw that one. Yeah, but then if they ever got you, you might need to go get a transfusion.
Like I said, we'll hang on for any other questions. Feel free to write them in the chat or unmute and ask your question.
Hey, Tom.
Yes, Joe.
Well, here's my question. When you use the words ordered and disordered,
Yeah.
in my mind, I think of control, uncontrolled. I think of enslavement, free, and then disorder would be freedom. I think of ordered as tyranny. I think of disordered then as emancipation.
Yeah.
Is that?
Well, I think
What's that?
I think that's. Go ahead.
No, that's.
Well, I think that, these are all concepts that we use in a variety of places in our life. I talk about this because I think it's important to understanding. You see where that discussion went about ecological restoration. And I find that misunderstanding that nature will somehow take care of itself, and we'll be able to eventually restore a prairie, and then we'll be able to walk away and the prairie will be able to take care of itself because nature can take care of itself. And nature, in effect, operated without people, but if those fragments of nature in a human world today can never take care of themselves because they will spontaneously begin to fall apart. And if we want to maintain it and keep them around in the world today, it means that we have to work to do that. So that's the reason for talking about that. I mean, and I think it's the wonderful paradox that we create beauty in a garden by ordering it, but the beauty of nature, which is of a different kind, evolves out of this very different organization that pleases our eyes in ways that are hard to describe. To look at a field of flowers or to walk in a forest that's has ferns, and that's a wild sort of disordered in the sense of the plants in my yard, but it's just sort of spiritually enriching experience. And just that I like the ideas of order and disorder because it gives us a different perspective on the world.
Incidentally, your quiz, when you said, what was it, Plotinus and Aristotelian, and I couldn't, I don't know how to chat, I don't know how to send a chat, but to me, I said switch because it was obvious that Socrates was the base. He was the trump.
You picked up on that, okay?
Okay, take care.
Thanks, Joe.
You're welcome.
Any other questions out there?
Well, thanks for indulging me. These were fun things. I've used them as chit chat things with college interns in the past and with classes when there was time to burn. And I love paradoxes. Maybe I'll use another one in a presentation one day. I love things that puzzle me, that I can't, that force me to think. And in that case, in the case of the Monty Hall paradox, I never could really think my way through until I actually tried it in a practical way. And then I thought, oh, it's so simple. But it's nice. If you look up the Monty Hall paradox, you'll find out that it stumped a lot of people a lot smarter than me. So it's a fun one.
Great. Well, I think that's probably it for the questions. So we'll just thank everybody for coming today. Our next time talk will be Thursday, March 31st. That will be on Darwin, the man who broke nature, from 10 a.m. to 12 p.m. again. So I hope to see you there.
Yes, I'll see you then. Thank you.